Hi everyone, and welcome to this video on section 7.3, separable equations. So in this video we're going to be going through a technique to actually solve these differential equations. So previously what we've been able to do is numerically try to understand solutions, graphically try to look at families of solutions, but now we're going to find a method to try to solve some of these. So the big idea here comes from how the differential equation is given. So this method will work for us if we can put our differential equation in this form. And the whole big thing here, separable, is I can separate the x's and the y's into two functions being multiplied. This is very important. So what are you looking for here? I can take all the x's and y's and separate them into two pieces, two chunks, a g function and f function, and this is multiplication. So, what's a common thing you might have to do? It mentions it here. You might have to factor, right? So I could give you a differential equation and it could look like no way it's going to be this way, but you gather up all the terms, you try to factor, it is a function of x and a function of y multiplied, and then we can go. So it's very common you're going to have to factor things, you might have to divide things from one side to the other, so we only have the derivative on the left, but that's it. If you can get it into this form, then we can try separable equations. And the way this works, basically, what we're going to do is once it's in this form, what we're going to do is we're going to do this. We're going to say all the y's on the left, and then we're going to say all the x's on the right. And the format that you end up getting here looks like this. So again, we have this, we've separated it. See dy up here? That tells me take everything with a y over here, move it over, algebraically like you would, divide it. X on the bottom here, I don't want that, I want it on top. You can think of multiplying this over to get the dx up here, and it ends up giving you this as your second step. So usually step one would be, factor, do whatever you have to do to get it of this form. Step two is going to be to, get all the y's on the left, all the x's on the right. And then step three is to integrate both sides. And that's how it goes here. Now, there can be extra steps. So, depending on the problem, we'll do some. There can be extra steps. There could be initial conditions. There could be some algebra so that we could make this y is a function of x. Some stuff with x's. Not always though. So sometimes that's 4, but only sometimes. We might end up getting something that we can't solve for y, and that's totally fine. But sometimes we can, and we'll try doing that. So you'll see an example. That's it. That's the whole thing. So you're just going to follow these steps. Factor out however you have to do it to make sure this is multiplication. All the x's are together, all the y's are together. Then get all the y's on the left, x's on the right. Then integrate, and then maybe do algebra depending on the problem or initial conditions. So we have this problem here. dy dx equals x e to the negative y. So already I see two functions, right? This is where the x's are. This one is where the y's are, and they're being multiplied. Perfect. Now, so step one, we're actually already done with step one. Step two then is going to be all the y's on the left, all the x's on the right. So on the right we'll have x dx. Just, you could think of taking this and moving it over. On the left though, we have e to the negative y. So we could divide that, but really it's not that bad to think about what will happen there. This is just going to end up being e to the y dy. Alright, so just as like a little side thing, 1 over e to the negative y. Well, I can move this up, make this negative. Negative, negative is positive. So that's our little side note. Okay, so boom, that's step number 2, right? What was step 3? Step 3 was integrate. equals integral. And you know, this isn't anything crazy. This is just, we know how to do this. The antiderivative of e to the y is e to the y. And then we're going to have to talk a little bit about this. So this might seem a little bit weird, but we'll talk about what happens. But this is general, right? A general antiderivative. So we've got some c here. Okay, and now antiderivative, x squared over 2. But then this one has a c, right? This should have a c. So we'll call that c prime because we don't know anything about these. They're just arbitrary. No reason they're the same exact c. But, so you're looking at that like, oh, that's weird. But here's what we're going to do. E to the y equals, and you don't have to do this every time you do a problem like this. I'm just going to show it to you one time. C prime minus c. Now, here's the thing. This right here, c and c prime are arbitrary numbers. Can be whatever. All these different possibilities. So when I subtract them, I just get another arbitrary constant. It's still arbitrary. So what you end up doing in a problem like this is you take this and just replace it with c. And I know you might be like, well, aren't you kind of abusing notation here? You could call it d if you wanted. It doesn't matter. It's still just an arbitrary constant. So if you ever end up in a scenario where you're doing two antiderivatives here, one on each side, or you're doing the integral, one on each side, they're both going to get a plus c because, of course, there's no bounds, but there only needs to be one constant here because you can move them together and absorb them into just one arbitrary constant again. And there you go. Boom. Solved it. So, okay, you know, well, you might look at this and be like, okay, yeah, sure, it's solved, but like, can you get this in terms of y? And so that's where we now jump into like that step 4 that we had mentioned with the question mark. You know, can we solve this for y? And in this one, you know, we can give it a shot. So e to the y equals this. So okay, well, we can natural log both sides, right? E to the y, what do we know about e to the y? E to the y is always a positive number, never 0. So just doing the log of that is all good. That's totally fine to do. Log both sides. Okay. Boom. All right. So, okay, then these cancel and we get this. Okay, so, you know, we actually could figure out what's going on here. We could plug in different c's. We could have different constants that would give us different equations here, right? So basically, any point you want to pick in x and y, we can find a c that's going to make this equation work. So you see that here for a few of them. These are all of the different versions of this solution with just different c's plugged in. But, you know, we don't need to make this picture or anything. It's just in case you kind of want to see what's going on. Totally fine. You can do that. And if you're really interested, you could plug in a couple numbers here and just kind of see what happens, right? Like you could go over here and you could plug in, assuming these are jumps of 1, you could plug in something like, oh, here's one, sorry. So you could plug in 0, 1. Okay, what's the solution that's going to go through here? Well, plug in. We're going to get 1 equals natural log of 0 plus c. 1 is equal to the natural log of 0 plus c, which I don't have to say again because obviously that's just c. Okay, so then we just have to solve this, right? The natural log of what will be 1? Well, c is going to be equal to e to the 1. So, altogether then, if I knew that this point was on my solution curve, then my actual solution curve is just given by this. So you're done here. But I'm just showing you this is an infinite number of solutions. I could just draw picture, 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 picture. I can pick out specific ones by just supplying a point. You're just going to tell me one point on here and I can pick out one curve. But if you don't, then I have an infinite number of curves that can be picked out. So just as a tiny little example, but for this problem, you could stop here. All right, So hopefully that wasn't too bad. Separate, integrate, you're good. All right, let's try this one. So this one, not quite in the right form for the original piece, but it's actually because this has already been almost fully separated out for us for step 2. Look, all the y's on the left, almost all the x's on the right. How do you kind of figure out what's going on? Rewrite this as dy dx. Then you see, ooh, I've got all these y's, good. I just need to move the dx over. So this is going to end up being y sine y dy is equal to x cubed dx. And then we have to just take the next step of integrating. So y plus sine y, we're going to integrate this. Integral of x cubed dx. Okay, so we can do this. This isn't too bad. So this would be y squared over 2, and then the antiderivative of sine is going to be negative cosine. And then remember, you could do the plus c here, but we're just going to put it on the other side. Equals x squared over 2 plus x to the 4th over 4 plus c. And there you go. Okay, good luck solving that one for y. Not going to happen. So that's fine. We just leave it this way, and if we wanted a specific solution, you just need to give me a point. I plug it in here, I can find c, and I know exactly what my solution will be. And just to kind of like check this out, you can pick out some of these pictures, see what the pictures look like, and some of them are pretty cool. So you've got this curve, and then you've got these curves. So it should be pretty clear from this then there are some solutions that are not y as a function of x. This solution looks like, okay, y could be a function of x here, y could be a function of x here, but these specifically don't pass the vertical line test. So that's why, you could think of that kind of like, that's why this is stuck in this form. That's not too nice. Because we have some solutions, curves that are just not y as a function of x, which is fine. So got some pictures there. But that's it. That's how you do this. You separate, you integrate, you're done. Okay, so let's do an example with what's called, again, an initial condition. And this is just going to add an extra step. That's it. So still, forget about the initial condition to start. Let's separate all the y's on the left, y dy, all the x's on the right. So this would be, move the dx over, ln x over x dx. Okay, now do your integration. Y dy, ln x dx. Okay, this one's not too bad. Y squared over 2. And then the other side, we actually have to do a little u sub here, right? U is ln x, du is 1 over x. So then we can plug in back into the integral, see what we get. So this would be the integral of u du. We can do that. That's going to be u squared over 2 plus c. Okay. And then we got to go back to x's, right? Y squared over 2 equals, and then that's going to be natural log x squared over 2 plus c. So this right here is our general solution. It's our general solution. It's a whole bunch of them. Depending on what point you're at, I'm going to get a bunch of different solutions. But we want a specific one, right? So this is where the initial condition comes in. That's y of 1 equals 2. And that's telling me, okay, I want to be at the point 1 comma 2. So do that and tell me specifically what the formula is, the equation is for the one single function that passes through that point. So just plug in. 2 squared over 2, my y goes in, equals natural log of 1 over 2, this is squared, plus c. Well, log 1 is 0, that's pretty nice. So this whole thing is 0. So that's going to be 4 over 2 is 2, equals 0 plus c. C is 2. So then my specific solution is going to be y squared over 2 equals log squared over 2 plus 2. And there we go. Boom. Okay. So hopefully that's not too awful. This is what that curve looks like. And there you go. Hopefully not too bad. So what did we do? Separate, integrate. We have initial condition, plug it in to find C, get your equation. That's it. Separable equations. All right. So this last one here is just a kind of like fun one. This says find the function f such that the derivative equals that. Now, this you might look at this kind of being like, whoa, this is pretty crazy. But we're in the separable equations section. Why don't we just try seeing if, this is something we can deal with. So I'm going to bring this back to what we were doing. I'm going to call y f of x. Now this equation is dy dx, so that's f prime is y prime, but I'm skipping a step here, equals y 1 minus y. Okay, so cool, we can deal with this, right? So this is going to end up being dy over y times 1 minus y. So all the y's on the left is dx. Again, like, all right, okay. So then we're going to integrate, right? So integral 1 over y times 1 minus y dy equals the integral of just 1 dx. So you're like, all right, maybe this is a little weird, but that's fine. I can do this. Right-hand side is going to be x plus c. Okay. Left-hand side is kind of like, uh-oh, what's this going to be? And this we can do using partial fractions, right? So a over y plus b over 1 minus y. We want that to equal, so just we're doing this now, 1 over y times 1 minus y. Okay, so then remember how this works. You do this cross multiplication, so b times y plus, and then we have a times 1 minus y. That's going to be the top of this new fraction, has to be 1. So remember, in partial fractions, right, we need to combine these two to equal this. So you got to multiply there, multiply there. So then by minus ay needs to equal 0. Why was that? Because there's no y's over here, right? So that's the same thing as saying b minus a needs to be 0. And then our next equation then, there's actually no b attached to any number here. So then it was just going to be a times 1 equals 1. So this is actually a pretty simple one. A equals 1, which means that b minus 1 equals 0, b equals 1. So, okay, that one wasn't too hard. So this left-hand side then will become the integral of 1 over y dy plus the integral of 1 over 1 minus y dy. Okay, so then how do we do this? Well, this is just log y, and this was going to be a negative natural log 1 minus y plus c. But again, remember, we don't need the plus c because we already have it over here. Also, negative pops out. You should do a u sub here technically, and you have this negative on the y. That's why that pops out. Just be careful there. So then all together, this is going to end up being log y minus log 1 minus y, right, equals x plus c. Look at that. So we've got this now, okay. And we know that f of 0 equals 1/2. So we have an initial condition. So that's f, which remember was y. F of 0 is 1/2, which is the same thing as saying y of 0 is 1/2, just to keep it in y's and x's for us. So it's going to be log, right? And then we can simplify this actually. This is 1/2 over 1/2 equals 0 plus c. Natural log of 1/2 over 1/2 is just 1. So you're thinking, oh, this is simplifying nicely. Equals c, c equals 0. And so all together, we have natural log of, and then you can combine this if you want, y over 1 minus y, right? So just again using log rules, equals x. Okay, now at this point, we're kind of stuck here a little bit because this is a good place to start, right? But we wanted to find a function f, and we haven't found that because it's still packed in here. So we have to try to see if we can solve for y. So let's bring down what we have, log of y over 1 minus y equals, we have over here, just x. Okay, so let's think this through. How do we get rid of the log? Let's everything. Y over 1 minus y equals e to the x over here. Okay, so then we can cancel these. We have y over 1 minus y equals e to the x. Now let's try to break all these y's out. So this is going to be y equals 1 minus y e to the x, multiply, because again, we want to get y by itself. So it seems like we're kind of messing things up here, but don't worry, we're going to get there. All right, put all the y's on one side. Okay, factor 1 plus e to the x equals e to the x, and divide. And would you look at that? We have found it. Boom. That was a little bit crazy, but we get there. So how did we attack this problem? We said, okay, this is actually just a differential equation, so let's separate, integrate, and then we got down to this formula, and in general, right, after we've plugged in our initial condition, like this, in a general problem, that we're just done. But this problem was specifically saying, I do want you to solve for y. Like, no, you got to solve for y here. And so we solved for y. So that's it. We've gone through a bunch of examples, even a crazy one at the end, and it always came down to you separate, you integrate, and then if you have an initial condition, you can plug in and solve for a specific function. And sometimes you can also just try to solve for y. But not always necessary. Just read the problem, see what it asks for. So if you have any questions, let me know. Otherwise, I'll see you in the next video.